Hi, hello. Welcome to the last section. It's crazy. It's crazy. I can't believe that we are already here at the end of the summer. It feels like just yesterday. Y'all were the little Orgo ducklings, and y'all were like waddling into crevices in the earth, and y'all were like being scooped up by hawks, and now you all are like about to take flight and leave and go in the quack, quack. That's y'all. I don't know. Anyway, game plan for today is to get through as much of the PISA as we can by learning Lecture 10. So I assume that no one knows anything about Lecture 10. Like, Lecture 10 didn't happen. Yeah. Like, I'll move some arrows, but again, it was another lights on, no one's home situation. So we're going to talk about basics of the enolates. We're going to talk about our two big reactions of the aldol and the clazone. And then we're going to talk about some other reactions that it can do and some kind of ways that it can get a little bit more complicated. But any questions before we kind of jump into section proper? Any logistical things? You feel like you know how to get through the next week and like what's due? Yeah. I don't know. I don't think so. But please come. Yeah.
Is there a review section?
No. Well, because it's me. Like yeah. And I would say it's kind of a cross between a lecture and a section. Like it's using kind of lecture notes, but I'm delivering it, so it's going to be kind of like section 8 vibes. I'm also hoping it won't take the full 3 hours. I'm hoping it'll be closer to 2 or 2.5, depending on how things go, how many questions there are. But yeah, we're going to do kind of a big recap of everything and be working a lot of problems, hopefully. So, cool. Yeah. Oh, yeah, it normally is. Thank you for catching that. Yeah. I normally try to do it so much better. My God. I hope it wasn't like that. I think it was the fire alarm went off in this building earlier today. And so I think it was bad for the middle section, but good for the first one. But, wow. Our moody lighting. Cool. So, anything else before we jump in? Okay. Well, the other thing is I do have these kind of, topics, heading outline. But the other thing I tried to do was like structure this by big ideas, just because like Lecture 10 to me feels like a big sea of a lot going on. And so we're going to kind of come back to some like core ideas to help keep us grounded. But without further ado, let's jump in. So, first big idea. Alpha hydrogens to carbonyls are acidic. So normally an alkane pK would be about 50, but the pK of these hydrogens at the alpha position, so if we have a carbonyl and go 1 over, that's the alpha position, their pK is about 20. It's way more acidic. Why? What's the answer to 90% of the questions in this class of why? Joseph's on it. Resonance. So if we deprotonate here, actually we can do resonance and push electrons up to the O. This makes a new functional group called an enolate. So it's like we have an alkene, and then we have this O- here, and it has resonance. And that's stabilizing the negative charge, spreading it out. Now, when we make an enolate here, this actually has a molecular orbital requirement. Kind of like for E2, we have antiperiplanar. So to make an enolate, we need the sigma CH to be parallel to our pi star CO. And it's so that the electrons can flow right in and it can start to do resonance. You can kind of imagine it as if it's not in this orientation, very briefly, you have a C with a negative charge that's not doing resonance, very briefly, until it kind of rotates into place. And this would never really form because its pK is like 50. So the only way that you can get that pK down to like 20 is for the hydrogen to be able to rotate like this and line up. We don't worry about this most of the time. This is something that comes up a lot more in Chem 27 when you talk about like this MO requirement, the enzyme that's holding it has to hold it in this very specific way to get this overlap. But we're going to see one challenge problem that deals with this, and we're going to work it in section today. So big idea number 1, alpha hydrogens to carbonyls are acidic. Big idea number 2, enolates are nucleophiles at the alpha carbon. This is big, y'all. This is huge. We have new ways of having carbon nucleophiles. Up until this point, we've only had a few. We've had like the alide in the Wittig reaction. We've had the organometallics and like Grignards and stuff. We've had nitrile doing SN2, and then what was our one other way of making carbon-carbon bonds? It's escaping me. But we've only had a few ways of making carbon-carbon bonds, and now this enolate is going to make carbon-carbon bonds left and right. It is going to get up to no good, make a bunch of carbon-carbon bonds. And the hard part is carbon-carbon bonds kind of blend into the background of our molecules. They make it hard to see which bonds are made and destroyed, mostly because a carbon-carbon bond is not really a functional group, right? Like a lot of other reactions are much clearer because it's going from this functional group to this one. And so we're going to need some more tools, maybe some more functional groups, in order to help us diagnose what's going on. The other thing is it's always going to be attacking at this alpha carbon, adding something to the alpha carbon. You are never going to have your enolate oxygen attack. Think about it this way. Oxygen's actually pretty chill with a negative charge. But the resonance structure here, where you place the negative charge on the carbon, that's not very chill. She does not want those electrons. She's going to be more likely to go and attack. Now, we do want you to draw the attack like this, from the enolate pushing from the O. We do not want you to do enolate things like this. Some classes do let students do that, but why is this not preferred? It's not even octet. Like, this does have an octet. It's not your most stable resonance charge or resonance structure, because this one's going to give us a better idea of the actual bonding of the molecule. That's why we like you to draw it this way. I have two little side notes here. One is enols versus enolates. This is kind of the difference between alcohols and alkoxides. So enol comes from alkene, alcohol. It's neutral. And then if it's negatively charged, it's an enolate. We had this 8 ending for negative charge. And we can do a lot of this chemistry in either acid or base. In everything I'm going to talk about in section today, except for one of the final examples, we're mostly going to be defaulting to base conditions, but you'll see on the P set some acid ones, and they're going to pop up. They are fundamentally doing the same things. The only difference is like our protonation states. But just to kind of make things simpler today, I've chosen to make everything base focused. So enolates versus enols, which do you think is a better nucleophile, an enolate or an enol? An enolate, why? I mean, they both have resonance. So, good first line answer. But why is an enolate a better nucleophile than an enol? Say one more time. Yeah, she has more of a buildup of charge, so it's easier to attack. It's the same reason why OR minus is a good nucleophile, but HOR is a much less good nucleophile. This is like too kind of stable. There's not a huge buildup of charge. So, cool. Enolates are a stronger nucleophile. The other thing that we have is, we call it the keto-enol tautomerization. So has anyone heard this word tautomerize or tautomer before in like another context? I think I encountered it in like a maths class and like a proofs class. So basically a tautomer is something that's equal. And if we look at a ketone here in the enol, they actually have the exact same molecular formula. So we're kind of saying that these two things are just two different versions of the same thing. It's like our Sandshrew and our Alolan Sandshrew Pokemon Pikachu. So they are really kind of the same, but just a slightly different orientation. Now we can go back and forth between these in either acid or base. And so the only difference is what we start off with. Like in base, we do our alpha deprotonation, then we neutralize here at the O. In acid, we protonate the carbonyl first, and then we do our alpha deprotonation. So just changing the order. So we can go back and forth. The other really powerful thing about this, as being the dual personas, or the Dr. Jekyll, Mr. Hyde, is carbonyls, are they typically nucleophiles or electrophiles? They're typically electrophiles, and most of the lecture 3, lecture 5 stuff we saw. But we're saying that actually she has this different form where she's a nucleophile, and that's pretty powerful. But we have a lot of different versions of enolates. So let's meet them. Choose your fighter. You have an aldehyde enolate, a ketone enolate, an ester enolate, dicarbonyl enolates. You even have nitrile enolates. Crazy. You don't want to run into her on the street. She'll mess you up. She is here to fight. What else? Enamines. But it just kind of ended, so I'll end it there. But we have all these different flavors of enolates that fundamentally are doing the same thing. They are pushing down, and then double bond goes and attacks, and this alpha positions the nucleophile. Enamine does the same thing, right? The other trends that you should know here, kind of theory-wise, is about pKa. And really, there are two kind of big trends. First big trend, dicarbonyls are way more acidic than monocarbonyls. So dicarbonyls, our pKa is around like 12-ish, and then monocarbonyls is around 20-ish. The other thing is, within these, as we go from aldehyde to a ketone to an ester, we get less acidic. So we should understand why. And the idea here is, an OR group, is that going to be electron donating or electron withdrawing? It's electron donating via resonance, right? So this thing already has a negative charge, and then you have something that wants to donate more electrons. So that's going to destabilize this. It's going to make this less stable, which is going to make this less acidic. Over here, an alkyl group, is that electron donating or withdrawing? Donating via hyperconjugation, the same thing that's stabilizing carbocations. So this is still donating electrons, so it's a little destabilizing. So this one's less acidic than an aldehyde. Aldehyde, there's nothing here to donate. So it is easier to have this negative charge because there aren't more things donating. If I had put like a fluorine here, you can imagine that that could be even more acidic, right? But then that looks crazy. An acid fluoride, she go boom. She go boom. So with this, again, our big trends, dicarbonyl is more acidic, and then if you have electron donating groups, you get less acidic. Let's see this in action with challenge problem 4b. So for paper users, I'm so sorry I don't have a printout for today, but everything that we are doing, except for these disconnections, are going to be in the problem set directly. So I would just encourage you to get out your problem set, and the disconnections are really quick, and you can just follow along visually for that. So challenge problem 4b, looking at this here, what functional group do we have on our arrow? We have an enamine. Excellent. Then over here we have a ketone and we have an alkyl halide, right? Ketones and alkyl halides, are those typically nucleophiles or electrophiles? Like a carbonyl, do you think of that as a nucleophile or electrophile? An electrophile. An alkyl halide, also an electrophile. A nucleophile can do like SN2 or E2 or something. Enamine, we have not really seen any reactions that start with an enamine other than enamine hydrolysis. We know how to make an enamine, but we haven't seen enamine's full family of reactions it can do. And so if it's mixed with a couple electrophiles, let's assume it's a nucleophile. And again, it's because it's really analogous to an enol. It's the nitrogen version of an enol. So what we're going to do is we're going to push in and have this go and attack. And then based on our product, does it look like we attacked the carbonyl or the alkyl halide? The carbonyl looks pretty much the same. And so I'm guessing that this carbon got connected to this carbon somehow. So let's attack this alkyl halide, and we are simply doing an SN2. If that was a stereocenter, what would happen to that stereocenter? Inversion, right? Okay, so that makes this bond between the alpha carbon and the enamine and the SN2 carbon electrophile over here. So then we have an imine, and we're going to a carbonyl. Is that a reaction you've seen before? What reaction? Bless you. What lecture was this on? Imine. 5. And what was the only reaction in lecture 5 that started with an imine? Hydrolysis. And you turned the imine into a ketone or aldehyde. So this straight up is amine hydrolysis. Lecture 5. So you can do all that mechanism. That's one that you ostensibly have locked and loaded in your memory from the exam. So again, this is how kind of some lecture 10 stuff can integrate with some of the earlier lectures. From here, we're going to turn to challenge problem 1. In challenge problem 1, it's a little bit more theory-based. So we're given the observation that one of these carbonyls has a pK of around 20, and one has a pK of around 40. Which of these is more what we would expect for alpha hydrogens? Silent answers, yes. 20, right? 20 is about what we expect for alpha hydrogens. So this is like expected. Alpha hydrogen. But around 40, that's kind of closer to like an alkane, right? So something's up. So take a second and draw in all the alpha hydrogens. So we have some alpha hydrogens in here. And this is the part where we actually do have to think about our MO requirement. Normally we don't, because these things can like freely rotate, but we're in this ring kind of situation, we can't. So our MO requirement is we need our sigma CH to be parallel to our pi star CO. So I'm going to draw in my pi star COs. And already on this left molecule, I'm seeing these two hydrogens are not parallel, right? They're like almost perpendicular to our pi star. Okay, well then let's look at this hydrogen. And we see actually this one does line up. So we have sigma CH that's able to donate into our pi star CO. So we can do a little deprotonation, make an enolate over here. So a base can come along, deprotonate, push in, push up, and we get to this enolate. Cool. Over here, though, we have an issue. Neither of these hydrogens can be parallel to our pi star system. These are both pointing like down and away, and so we can't, like, there's no sigma CH and pi star CO overlap. So we can't form an enolate. But even if we could, let's imagine hypothetically, we can break physics. We can break geometry. If we were to do this, this is what our enolate would be. And does this make you sick? Is this nauseating? Do you need to take a Dramamine? What's going on with her? Why is this bad? I need a little bit more volume. Yeah. Let's play Hangman. Oh, yeah, you got it. I was going to say give me a letter. But yeah. It's Brett's rule. Brett's rule is we can't have a double bond on a bridgehead atom just because of the geometric constraints of these like bridged rings. I shouldn't have assumed y'all needed Hangman. 11 o'clock needed Hangman, so. Cool. So that kind of explains this first one. The second one, we're going to touch the earth. What's different? What changed? Okay, why are y'all being coy? I know you see something different. If you see something, say something. What's different? Wait, say again. Well, the Turk butyl group's the same in both of these. I'm talking about like from starting materials to product. Oh, okay. Yeah. Sorry. What's different between these two? Spot the difference, gang. The D. Yes. Thank you. So, what was originally there? Well, there was a hydrogen, right? So this reaction, the only thing that changed is the hydrogen became a deuterium. Cool. So how does that happen? Well, we're in kind of enolate land. And this is a base, right? This is like OH minus, OD minus. So, if we look at this, do we have the right orbital overlap? This is our pi star CO. And we have our sigma CH. Sigma CH looks like it can donate into the pi star CO. So, let's make an enolate. OD minus comes along. Boop, boop, boop. Here, we have a tert butyl still there, we have our methyl still there, and we have this enolate. But then, what is our enolate attacking? Well, we just need to install a deuterium. So really, we're just doing kind of the deuterium version of an alpha protonation. An alpha deuteration? I'm not sure. But literally, we're just going to have our deuterated water, D2O. We're going to push down, we're going to grab a deuterium. Seems kind of silly. But maybe the actual better question is, why could we only replace that hydrogen and not something like this hydrogen? Why was that hydrogen not replaced? She's still there. Does she line up with the pi star? No. So we can't form an enolate. So she's still there. That's it. This is the question that requires the most thinking about this MO requirement. We don't typically test about it, but it's just wanting you to kind of engage a little bit more with that structure. And notice that we had to put these on rings if we were really wanting to think about this structure, because otherwise it can move and rotate freely. But any questions about this, of the kind of enolate basics? Alpha hydrogens are acidic, enolates are nucleophilic at the alpha carbon, and then we have this MO requirement. Ding dong. We need some caffeine. We need some music. Oh, well. So it's so bad. You know, most of these jokes are for me. I am out here cracking myself up, which is really annoying because when you see someone laughing at their own jokes, you're like, okay. But the next topic is pretty meaty, and so my transition is get ready.
This is my meal. I call this girl dinner. Girl dinner. Girl dinner. Girl dinner. Oh, girl dinner.
The aldol reaction is girl dinner. So our third big idea is enolates can attack ketones and aldehydes, and that is the aldol reaction. So in the aldol reaction, our electrophile is a ketone or aldehyde. We're going to be doing some Pavlovian conditioning today, some call and response. And one of the big ways to tell which reaction happened is to know what the electrophile is. So the electrophile of the aldol reaction are ketones and aldehydes. The electrophile of the aldol reaction are... The electrophile of the aldol reaction is... If we attacked a ketone or aldehyde with an enolate, we're doing the aldol reaction. If we attack a ketone or aldehyde with an enolate, we are doing the aldol reaction. Amazing. Cool. So, fundamental idea here. We make an enolate. The enolate attacks a ketone or aldehyde, pushes up, and then we neutralize her. When we do that, we get to our first product. This product, her government name, is beta-hydroxycarbonyl. because at the beta position, we have a hydroxy group in alcohol to our carbonyl. But everyone calls her aldol. You should call her aldol as well. The big thing to note is that this is an aldol at the beta position. Like, you can't have an aldol at the gamma or the alpha or the whatever. So this is a valid stopping point. This sometimes will be it. We will stop here. We've done the aldol. And we call this the aldol addition product because we've added the two molecules together. However, we can keep cooking it in our frying pan on heat and remove some water and do this condensation here, removing water. And then, who is she? Miss enone, our first functional group. We did all these reactions where we attacked an enone, but now we know a way to make an enone. Full circle. Full circle moment. Her government name, you might not have heard her, is an alpha beta unsaturated carbonyl, unsaturated biology term. And it is creating a double bond, which biologists call unsaturations. So again, just keep calling her enones. So this is our condensation product. So after we've formed the aldol, let's see what else we have to do in order to do our condensation. I'm about to show you the number one mistake students make on the aldol mechanism. You ready? You ready? So they're like, okay, I have my aldol. I need to get over here. Maybe I'll do it up here, yeah. They say, okay, making an alkene, elimination. So I'm going to go right here. I'm going to take my base, eliminated, done, iconic, fierce. What's wrong with that? Why is this no good? Alcohols are bad leaving groups. So we can't just do an E2 elimination. Never, never. That's one. Any other reasons? Yeah.
What if we just change the alcohol to a better leaving group? Then can we do that?
So you could, but that's having to do a whole different reaction. And this can still happen in the same pot. So there must be something else that's going on that can do this little elimination. That, like, it's not even something that we can do a lot of controlling of. You're right, we could do it to bromine, then we could do an E2. But we've added two separate reactions when this could still be happening in the same pot. So what really happens is we deprotonate and we make another enolate. That's kind of weird. But why do you think that we go this way rather than doing this? If we had to deprotonate this, make a negative charge, like if this is not a good enough leaving group, we can't just fold right in. So we have negative charge on carbon, and this is going to just do resonance. Like this is an alpha hydrogen situation. So part of it is like we're deprotonating alpha hydrogen, so we make an enolate, and the other part's the OH is a bad leaving group. And then once we have our enolate, we can do this kind of super lone pair push moment where we push down from the O, move over, and then kick off our OH. So this super lone pair push is good enough to kick off an OH leaving group. And we call this the E1CB mechanism. It's elimination. This step is unimolecular, the rate determining step, and it's the conjugate base of this acid. I call this water bending. So you know, like if you're in a pool, and like let's say there's like a frog in the pool and you want to get it out, what you might do is first bring some of the water towards you and then push it out in your little water bender, Avatar, Last Airbender. That's what we're doing. We're moving the electrons are water in this metaphor, moving the electrons towards us, the carbonyl, and then we're doing this super lone pair push of the electrons and kicking off the water, kicking the frog out of the pool, or like splashing your friend in the face. So, don't forget your water bending when you are doing girl dinner. Okay, so the other big framing, we said already that the electrophile was a big deal. That determines that this is the aldol reaction that we're attacking ketone and aldehyde. The other thing is making sure that we have quick associations of these products to this reaction. So the products of the aldol reaction are aldols and enones. The products of the aldol reactions are, one more time. The products of the aldol reaction are, woof! Okay. Say it with me, aldol, enone. The products of the aldol reaction are Good. I feel like Michael Scott in his improv class of like, I can't show you, but I have a gun. The products of the aldol reaction are aldols and enone. So if you see an aldol or an enone as the product in a mechanism, you know that you've done what reaction? The aldol reaction. Exactly. It's giving us clues to figure out what's going on. So let's do some practice. This is challenge problem 7 on page 16. I've abbreviated this whole big crazy thing as R, just like a little R group. But if we look at this, where can we make an enolate? So this R group is kind of like a benzene here. So do we have any alpha hydrogens over here? No, we don't have any alpha hydrogens. So can that be the enolate nucleophile? No, if we don't have alpha hydrogens, we can't make an enolate. So no, so this has to be the electrophile, which means this is going to be our enolate nucleophile. That also makes sense because remember dicarbonyls, they're more acidic, right? So what I want you to do is I want you to do an aldol condensation between these two. Just fully do this. You are copying and pasting curved arrows, but on these particular molecules. I'm going to give you like 3 minutes to write through that. Then there's going to be some last step here that we are going to do together. But I will leave this up so that you can see the mechanism. And again, this is challenge problem 7. How's it going? You have like 10 more seconds while I copy and paste something. So how did you do making your condensation? Any questions about any of the steps?
He said it doesn't look like that.
There's one more step that we haven't done yet.
Oh.
I was just saying first do the condensation.
Oh, okay. Like the eno has to look.
Yeah. Yeah. So, we have a new reagent, NABH4CN, NABH3CN, sorry. And she's a variant of our soft boy that doesn't even attack ketones and aldehydes. It only attacks enones and only attacks 1,4. So I often call him softer boy. So this is also kind of completionism of, didn't we have a way that NABH4 would only add 1,2 to an enone? What was that? CeCl3, right? That was a loose reduction. This is a way it only adds 1,4. So again, anything that you're like, how do we do this in organic chemistry? There is a way, we just haven't taught you because it can get complicated. So it's going to be exactly what you'd expect here. So we're going to draw out that BH bond, negative charge on the boron, and it does a 1,4 attack. And so this is just straight up conjugate addition where we push up to the O. And then the kind of cool thing is, all the way back in conjugate addition, look at what we made. We made an enolate. We weren't calling it that, but like that's what it was doing. And the second step in conjugate addition is an alpha protonation. So our enolate's going to go down and grab a hydrogen from our alcohol in the solvent. And there we go. Challenge problem done. Now, to talk a little bit about another challenge problem, 2A. If I was putting myself in y'all's shoes, budding organic chemists, I would think Grignard ketone. Lecture 3. I know this. I'm going to do the pH, MGBR, blah, 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 attack. Okay, my product. It's going to have the pH that we added, and then it's going to become an alcohol. Done. That's not what we have. Oh no, what has happened? It's all gone to crap. Okay, where did this benzene come from? Where do we have benzene in any of our reagents? The pH, weird, okay. And then I see this R group, right? And I see, ooh, there are 2 of them. So that means that we must have glued 2 of these molecules together, right? Moreover, what functional group is this? The trepidation. It's 1:30 p.m. What do we gotta lose, folks? Be wrong, be loud. It's an enone. And enones are made via what reaction? The aldol reaction. I love I say be loud, people whisper. And I guess compared to silence, it is loud. Okay, so we have this. We're doing an aldol. We see also 2 equivalents of these. So if these are carbons 1 and 2, that will probably be 1 and 2 over here. So if we're doing an aldol reaction, it looks like it's just an aldol reaction between 2 of the same equivalents, right? So one of them needs to be made into an enolate. If only we had a base. If only we had a base. Do we have a base? What's the base? The Grignard. Honestly, I feel like this class has been us just like the subliminal message that we've been trying to get you to take home is that Grignards are basic. I feel like it's kind of like a soft roar throughout the back of everything. Grignards are basic. Grignards are basic. Grignards are basic. And so what we're going to do is instead of having our Grignard go and attack the carbonyl, we're going to have it just deprotonate here and turn it into an enolate. When that happens, our phenyl group's going to grab an H, and that's just benzene. Okay. From here, our enolate can go and attack another equivalent of that starting molecule. And this is straight up the aldol reaction. An enolate attacking ketone or aldehyde. So, exact same curved arrows that you just did above. Any questions about these kind of like basics of the aldol reaction? Okay. So, next big idea. The exact identities of these starting materials result in variants of this reaction. The curved arrows are exactly the same, but it's going to look slightly different. So I refer to this as the aldol diaspora, Our classic aldol reaction, the first one that was discovered, was the molecule attacking itself. So it's just like that example that we just saw of two equivalents of the same molecule. One's turned into an enolate, it attacks itself, make a product. That's their classic aldol. But also, we could attack a different molecule, a different ketone or aldehyde, in which case we call it the crossed aldol. Then, if they're on the same molecule, it's intramolecular. But also, powerful fact, all of this is reversible. All of this with aldol reactions are reversible. We have the retroaldol, and I'm not going to talk through it because it's literally beat for beat the reverse. Last step here, you push off an OH. Now the OH comes and attacks. Then before that, you did a deprotonation. Oh, you do a protonation. It's straight at the reverse. You want to get to where you can do the aldol and the retroaldol back to back to back to back to back 20 times in a row, upside down, blindfolded while sleeping. That's her. So we have all this. The thing that I feel like has been under-discussed in the literature is understanding the aldol diaspora in terms of its cha-cha slide concordance. So I know that you all are familiar with the cha-cha slide, yes? Little nods. Cha-cha slide, have you heard of her? Is that too dated at this point? Anyway, the first one, because they're the same molecule, it's, of course,
slide to the left, slide to the right.
They're the same molecule. Crossed aldol. Anyone want to take a guess who she is in the cha-cha slide? Say again?
Slide to the right.
No. Slide to the left, slide to the right. They're the same molecule. I'm just moving it around. What's going to be the crossed one? Crisscross. Crisscross. Okay, so now hard, intramolecular. What's her energy?
Clap your hands.
No, I love the enthusiasm. I appreciate the loudness.
Them together.
See, I think about it as like it's doing a little wiggle into itself. And so to me it's
Cha-cha, real smooth.
as it like comes together. The other one that I think it is
Last time to get funky.
because it's weird. It's like it's the same arrows, but seeing it intramolecular always just feels weird, right? And then, of course, there's no ambiguity here. What is the retroaldol?
Reverse. Reverse.
Or it could be, take it back now, y'all. Either one. And so, to conclude.
Freeze. Everybody clap your hands. Come on, y'all.
I have a gun.
Check it out, y'all.
Ding dong. Cool. So yeah, I don't know, under discussed in the literature, maybe that could be a research project for one of y'all going forward if you're interested in doing more chemistry. But yes, all of these flavors, same exact curved arrows each time. So the last thing on the aldol that I want to discuss is this idea of, okay, if we are spotting the aldol reaction out in the wild, we want to be able to kind of work backwards and see what the nucleophile and electrophile were. So we need to be able to do disconnections on these, and we'll see it in practice and challenge problem right after. So what we do is, what are the functional groups we are scanning for the aldol reaction? Aldol reaction makes a blank and a blank. It attacks the ketone aldehyde, but what products does it make? Aldol and enone. Thank you. So we find our enone, and we label the alpha and beta positions. We find our aldol. We label the alpha and beta positions. And the way we do our disconnection is we cut between the alpha and beta position. When we do that, which side was the nucleophile? Was it the alpha carbon side or was it the beta carbon side? let's go back to key idea number 2. Enolates are nucleophilic at the alpha carbon. So when we cut, which side is the nucleophile, the alpha side or the beta side? The alpha side, amazing. And so our nucleophile we know is an enolate, so let's turn that alpha side into an enolate. So the alpha side becomes an enolate over here. And then the beta side, what's the electrophile for the aldol reaction? What's the electrophile for the aldol reaction? A ketone or aldehyde. I'm going to keep asking it until it becomes like a gut response. So maybe write that down in the corner of your little paper or iPad. The electrophile of the aldol reaction is ketone or aldehyde. The products formed are an aldol or an enone. Ding dong. And then we can take this enolate back even further and see it probably came from this carbonyl. So this is just a classic aldol where two equivalents are attacking each other. For our aldol over here, we can cut in between it, the alpha and beta position. And on the alpha side, that's our nucleophile side. So our nucleophile side, we make our enolate. And then our beta side, our electrophile, is going to be an aldehyde in this case, because there was already an H on here. And then from that, we can take it back even further to the carbonyl version. Work. So try this out on your own. Find the aldol or the enone, label alpha beta, cut between it. See how it goes. So where is our aldol or our enone? Her? Is that an aldol? That's an OH at the alpha position. That's not an aldol. Aldols are at a beta position. Okay, so that's not it. Is that an enone? No. So
You want to go in for some water?
do you want to cut the aldol? The enone? Okay.
Check down.
Trick job. Trick job. So if we look at this, there is no aldol. There is no enone. So did we do an aldol reaction? Trick question. No. So if I go in here, there we go. Trick question. Not her. Yeah.
Would you mind just repeating how you knew that the previous one was an aldehyde next time?
Yeah, it's because here in the beta position, you have a hydrogen. So if it has a hydrogen on it, it came from an aldehyde that we attacked. And if it has like another carbon on it, it came from a ketone. Yeah, totally. So, sorry to trick you, but let's put this into action in an actual way. So in challenge problem 3A on page 12, we see what functional group in our starting material? What new functional group do we see in our starting material? Aldol. And this is the thing, just like we said for like an enone, we can't see it as an alkene and carbonyl. We have to see these as connected. These are the new functional groups that you need to know for lecture 10. So here we have an aldol, our alpha and beta position. And then what functional group do we have in the product? Well, we have an enone, alpha and beta, right? So with this, normally going from an aldol to an enone, that would just be like continuing in the aldol reaction. But if we did that here, we would make this enone, right? And that's not what we have at all. So something weird has happened. So what we're going to do is let's undo this aldol. Let's cut here between the alpha and beta position and draw what that nucleophile electrophile looks like. So take a second, try to do that. This is challenge problem 3A on page 12. And this can be in your kind of planning towards the top of the question. Remember, the alpha side becomes the nucleophile, the beta side becomes the electrophile. So over here, we have our enolate on the alpha side. On our beta side, we have a carbonyl. So here, it's like we covered this up and replaced the OH with a carbonyl. Okay, then let's also disconnect on our enone and see what came before it, as if that we were going to do like an aldol reaction. On the alpha side, we have our enolate. And on our beta side, we have our carbonyl. Interesting. What do you notice about these? Like, these are both 7 carbons long, and they both have enolates, right? They're both 7 carbons and they're both enolates. They both could be made from this molecule, right? This straight chain. If we had done something like push down, grab a hydrogen, here, we'd get to this neutral intermediate. And then over here, we can deprotonate, and we can make this enolate. But those enolates are not the same, right? One of these over here is the enolate that's made if you deprotonate at one of these internal carbons. But then the other one is the enolate that you make when you deprotonate at one of these external ones, the terminal ones. And so it looks like the logic of this reaction is you did a retroaldol. You undid part of an aldol reaction, got a straight chain, and you went from your initial enolate to a different enolate. And then you did a normal aldol reaction. So this is now a different aldol reaction from the one that we started with. The energy of this, to me, is very much the like Dance Dance Revolution Rasputin dance, like the. So it starts out, and I'm an aldol over here, and then it's like, actually, I'm a straight chain. What'll I be? Will I go to the left or the right? Which way? And then it goes, I'm an enone over here. So it's changing which side that it's making its enolate on. I love this question. It's my favorite question on the problem set. I think that this is a great exam type question because it makes you think about the reverse reaction and the forward reaction. It's making you think about intramolecular, not putting on the glasses. Okay, better lock in. It's an exam question. It's making you think about the forward and the reverse reaction. It's making you think about these intramolecular ones, making rings. And you really have to know the reaction kind of forward and backwards to do this. So I really like this. This is challenge problem 3A. 3B is going to be the exact same thing, but with a Claisen reaction. So we'll touch on that. Any questions here about aldols? I know we've spent a lot of time on aldols. Next big idea, number 5, enolates can attack esters. And when we attack esters, we're at the Claisen reaction. So, wait, aldol reaction, who did we attack? Ketones or aldehydes, thank you. And now if we attack an ester, we're doing the Claisen reaction. So let's look, enolate attacking ester. What we get at the end of the day, our product is called a beta dicarbonyl. So we have 2 carbonyls that are alpha to each other, that are beta to each other. Ugh. It's sometimes called a 1,3 carbonyl, but beta dicarbonyl is kind of our standard one. And you have specific flavors, like if one's a ketone, one's an ester, you have a beta ketoester. But beta dicarbonyl, I think, is the general umbrella term. So, wait, beta dicarbonyl, that's a new functional group. There have been so many. What were the new functional groups that were formed from the aldol reaction? An aldol and a enol. Hey! Oh my gosh, okay. Just takes repetition. Getting in the reps. So let's see, why is this different? Why, when we attack an ester, instead of a ketone and aldehyde, do we get an entirely different reaction, different products? Starts out the same. We make an enolate. Enolate attacks the ester. That looks the same. This is the step where it's different. When we attacked a ketone, for example, here we are locked. We don't have any leaving groups present. The best we can do is grab a hydrogen and neutralize this and make an aldol. But when we have attacked an ester, we have an OR, which is a leaving group, on our molecule. And so in a kind of Shakespearean turn of he was the king, he was a carbonyl, now reduced to an O-, he's going to reclaim his throne, but he has to sacrifice his oldest friend, OR. And he says, I'll do that happily. To be a carbonyl, goodbye. So this is the step. This is the reason why when we attack esters, we get a different product than when we attack ketones and aldehydes. So you're like, oh, I made my dicarbonyl, done. I don't think so, honey. When we make our dicarbonyl, we are still in strong base, right? We said that the pK of a normal enolate's like around 20-ish, but then we made a dicarbonyl. Are dicarbonyls more acidic or less acidic? They're more acidic. They're way more acidic. Their pK is around 11 pK, and this one was around 20. So if we are in base that's strong enough to deprotonate in 20 pK, we sure as hell are going to deprotonate our 11 pK acid here. So it is just something that happens. It has to happen. You can't stop it. Immediately once you form your dicarbonyl, we are going to form an enolate. And that's why we have to have an acid workup step for the Claisen. Because then if we want to get back to our neutral molecule, we have to reprotonate it. So these two steps together I call the annoying steps. And if you stop here and don't do the other things, it's -3 points. I went back and looked at my OChem 2 exam from the first time I took it, and I forgot to do the annoying step, but they forgot to count me off. So I got away with it. You won't. I'm looking for the annoying step because that's what it is. It is. So I even write like #annoying on the paper just to like remind myself that it's annoying. The other mnemonic that I have is, I can do this because none of y'all are named Claisen, but Claisen is sometimes like a name that people have. So I imagine a girl named Claisen who's super annoying, who won't stop talking. And I think Claisen, annoying, is friends with Esther, who we love. Esther, latte for Esther, double addition to Esther. Esther we know and love is around here. But that's my mnemonic for like Claisen reaction. Our electrophile is Esther. We make a beta dicarbonyl, and Claysen's annoying, so we have to do the annoying step. Aldol reaction, the best I could come up with good was like girl dinner, of like it's a big like meaty reaction, but here we are. So let's do a Claisen. So this is Skill Builder, page 10. Because it's Skill Builder, let's do it together, and we'll go a little bit faster. So firstly, we need to make our enolate. Does it matter which side we make our enolate on? No, it's symmetric, so it doesn't matter. So Naomi comes along and makes an enolate like this. Do I have too many peaks? No, I have a number of peaks. Cool. So now our enolate attacks an ester. So we're going to push down, attack an ester. When we do, we make a 1, 2, 3, 4, 5 membered ring, closing that loop. And then I'm forgetting this arrow. So I literally just draw a 5-membered ring, number 1, 2, 3, 4, 5. Carbon 1 is going to have this little dangly ester moment. And carbon 5 has now an O- and an OMe. The carbonyls fall from grace, but now Shakespearean Hamlet-esque reclaims the throne, kicks off OMe. And we're done. Easy. So much shorter than the Aldol reaction. Any questions? Really? No questions? Bang. And just like that, we lost 3 points on the test. It's so easy. We were walking through the forest. We fell in a pit. We're now like laying on spikes. What did we forget? The annoying stuff. Do you see how quickly it can happen? I just told you about it. It happens to the best of us. We have to be on the lookout. We sometimes have to be injured before we learn from it. But you don't get another exam to be injured before the final, so injure yourself with this weekend and then learn from it, and then don't be injured on the test. So we have to blah, 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 make our beta dicarbonyl. We have to deprotonate it. And it's OMe, sorry. Now this is kind of a subtle point. When we deprotonate, are we going to push electrons towards the ketone or towards the ester? That was a competent ketone. Why? Who said it?
The pKa is like or something. Like it's
Yeah, why?
the first box that you
Wait, yeah, why?
I don't know. Like it's
No matter who we push it to, we're pushing electrons towards it, right? Which one of these already has more electrons around it? The ester. The ester has resonance. It has something else pushing electrons towards it. And so when we're trying to figure out where to shunt these electrons when we deprotonate, it's going to go to the thing that has less electron density. So we're always going to go to the kind of ketone aldehyde side. So now we've done this. We've made an enolate. And just like that, we undo it. Hashtag annoying. The other one here is challenge problem 3b, which is the same as the Rasputin one over here. You're going to do some sort of retro Claisen, get to a straight chain, and then do a different Claisen. Slay. We're really trying to talk about every challenge problem. We're really trying to incentivize people to come to section. Cool. With that, very quick transition. We have the Claisen diaspora. We have classic Claisen, cross, intermolecular, retro, all the same. Retro Claisen, the reverse. This is the one that Logan pointed out in lecture students often mess up on. The first step of the retro Claisen, which is to attack a carbonyl here. It's kind of the reverse of that lone pair push step that we saw over here. The other thing that's kind of interesting with the cross Claisen, so remember, what makes a Claisen reaction a Claisen? It's the electrophile is an ester. The electrophile is an ester in the Claisen reaction. So we could have that our nucleophile and our electrophile are different esters, but our nucleophile could be any other enolate. The only thing that's important for making it a Claisen reaction is that our electrophile is an ester. So you could have an ester enolate attacking, or you could have a ketone enolate attacking. And it's all about what you're attacking that it determines which reaction that we are going to do. Retroclaisen here and disconnections. So what we're going to do is, what is the functional group that we are scanning for to see if there was a Claisen? What's the product functional group of a Claisen? You got this. I promise I don't have a gun. A beta dicarbonyl. Great. Cool. So, beta dicarbonyl, we spot it. But then the question becomes, do we number it like alpha beta in the green, or do we do it alpha beta in the blue? Does it matter for this one? No, it's symmetric, so let's just pick one. So I'm going to pick the blue, and I'm going to cut between the alpha and beta. So which side was the nucleophile, the alpha side or the beta side? Big idea number 2. Enolates are nucleophilic at the alpha carbon. So when I cut along the alpha-beta bond, which side's the nucleophile, the alpha side or the beta side? The alpha side. So that means the beta side has to be the electrophile, right? So on our nucleophile side, we make it into our enolate. Okay, heard. The electrophile, what's the electrophile for Claisen? An ester. So we need to turn this thing into an ester. It doesn't have an OR group on it because that got kicked off. So I'm just going to add like an OET, something like that. So that's how we disconnect. We can take this back further and see that this came from this carbonyl. But here, yeah, our nucleophile came from a ketone, but we attacked an ester, and that's why we got this product. It gets a little bit harder with something like this that's not symmetric. So do we want to cut alpha beta in blue or alpha beta in green? Which side was the side that is the kind of dominant one that like attacked? How do we figure it out? So this is kind of tricky, but we said the whole thing was the electrophile in Claisen is an ester, right? But when we attack that ester, her OR group leaves. And what does she become at the end of it? Not an ester anymore, but a ketone. Cool. So if we see an ester in our product, could that have been our electrophile that was attacked? No, it couldn't have been because it still has an OR group. It didn't get kicked off. So we know that this over here is the electrophile. So that means we need to cut this blue way to make this ester side the nucleophile. And again, it's because whichever ester electrophile was attacked, its OR group got kicked off. So we disconnect. Alpha side's the nucleophile. And the beta side, we need to turn into an ester. From there, we can go back even further to get our carbonyl version instead of the enolate. Cool. Okay, try disconnecting the third one. Find your beta dicarbonyl, and then cut between it, decide which side needs to be alpha and beta. Where's our beta dicarbonyl? Is it here? No, that's alpha. Is it here? Alpha, beta, gamma. No. Trick question. Oh my gosh. Oh my gosh. Bomb. And show the. Why is it doing all this? It's being weird. I want to add a bunch of emojis. How do I do it? She gets a one of those. She gets a. What's the auto predict? I love that. 2. Baby, no. And I'm glad you're feeling better. I wanted to just do, like, for the other one, I think I just did, like, this. I should just copy and paste. Trick question. So again, the thing is, we want you to be thinking about this, you know? Like, you can't just, like, execute something if you're not finding the right thing to latch on to. And training your eyes to look for beta dicarbonyls, to look for aldols, to look for enones, that's, like, the first step. Lecture done. Cool. Any questions on the Claisen reaction? So these are like our 2 big reactions in lecture 10, the aldol and the Claisen. They're the kind of huge ones. But let's get into some more nuance. That's the nuanced transition. So, I have a quick little problem that I'm going to give you a little time to think about. I'm going to give you like 30 seconds. What type of reaction does it seem like we're doing based on our functional groups here? This made an enone, so what reaction is that? The aldol, great. Okay, I want you to try to predict which of these is formed. So, I'm going to give you some thinking music. So, who has a take? Which one do you think is formed? Be bold.
D.
D. Why? No, I'm not discouraging. Sure. Why? Cool. Anyone else? Yeah. You almost said something. You have to now.
It's B.
It's B. Why? I'm going to lose my mind. Anyone have any kind of reasoning as to why one of these might be formed?
When in doubt, pick B.
Anyone else?
It's probably in the notes somewhere.
That's my time, folks.
It can't be one of those that only has red and orange or green and blue.
Unless it's a trade.
You said you wouldn't put the answer in the center. Like, yes. There's no reasoning? Yeah.
I think it's D.
Sure, why?
Because you're losing one oxygen, and like knowing where the oxygen's coming from, my guess is that I just don't think B makes sense because like where is that falling into? I don't know.
Oh yeah, for sure.
Does it have to do with stable carbocation for creation?
You make better alkene by doing B if you do B.
That's closer. That's in the realm. Where did a carbocation come from? We said we were doing the aldol reaction. Zaitsev, that's a good thing to think about. Yeah, so we're making an alkene, like, more substitute alkenes are more stable. But also, all of these are fully substituted, right? All of them have no hydrogens on the alkene. So maybe that's like a ding against A and B. So, all of them are formed. If we tried to execute this reaction, every single one. So none of you were wrong. I just wanted you to think. So, like, if you made the enolate on the outside and attacked a red one, you get A. If you made it on the outside and you attacked the blue-green one, you get B. If you made the inside enolate, you would also attack either one, get the two more products. But then you could have made your enolate on the blue-green one. And then you could have attacked either one. You can make it on either side.
Is there one that's more favorable than the other?
I mean, maybe slightly, like more trans things. So I'm like, E puts these two big groups trans to each other. Or like A, like maybe a little bit more. But no matter what, you're going to get a mess. Like, how do you go about isolating these? These are all going to be in the same pot. So, big idea number 6. There's a lot of chaos that can happen. How do we control the chaos? We need some strategies. So, one strategy is using symmetry. If we have a symmetric molecule, then we are going to have the same enolate on either side of our carbonyl, and then we get half the products immediately. We can also use one-sidedness. So if we put something like an OR or a phenyl group or a tert-butyl group or we make an aldehyde, things like this, there's no alpha hydrogen there. So there's only one side that we can use to make our enolate. So that also helps control the chaos. We can also have versions where we have no alpha hydrogens on either side. So if we have no alpha hydrogens, can this become an enolate? No. So this must be electrophile. Other things that we can do are related to ring size. So like let's say you have these outside enolates or these inside enolates. The inside enolate, if you draw it all out, that's going to make a 6-membered ring, whereas the outside one's going to make an 8-membered ring. And preferentially 6 and 5-membered rings are the most stable ones. So we are going to prefer to do this and make that enolate. Same thing over here. The inside one now would make a 4-membered ring, and the outside one would make a 6-membered ring. Then over here, the inside one would make a 5-membered ring, and the outside one would make a 7-membered ring. So that's another way. If you're going to take the MCAT, you might see this reagent called LDA. She's just lithium diisopropyl amide. She's a really strong base. But the other strategy that you can do, we don't really do this in this class, is you can convert all of your carbonyl into enolate, and then dropwise add in your electrophile. And that helps kind of control for the chaos of like choosing which one's your nucleophile, which is your electrophile. But again, this page was just like nuance. How do we control the chaos? Getting to think a little bit more about it. So thank you for your participation. Last one. Big idea number 7. Enolates can also do other things. So like all throughout this course, you've been learning all these different functional groups as like nucleophiles and electrophiles. And really lecture 10, the core idea is enolates a nucleophile. So we said for the aldol reaction, enolates attacks ketone aldehyde. For Claisen reaction, enolates attacks ester. And attack other things. If you use an enone electrophile, then it does 1,4 addition. An enolate does. So enolate can add 1,4 to an enone. And our product that we get out of it is a 1,5 dicarbonyl. 1, 2, 3, 4, 5. And that's just by virtue of when we attack at the 1,4 position, we create this space between it. So 1,5 dicarbonyl is a new functional group that you need to be on the lookout for to spot this reaction, which we call the Michael addition, just attacking an enone. Then enolates can also do SN2, you know? Like if you have an alkyl halide as your electrophile, you can literally just have the enolate do a backside attack. Bada bing, bada bang, you've added an alkyl group at the alpha position. This one is not quite exactly an enolate attacking something, but it's like a related reaction of a decarboxylation. So if you made a beta dicarbonyl, this is the product of what reaction? The Claisen, the beta dicarbonyl, that's our product of a Claisen. And what you can do is if you use NaOH and H+, this does an ester hydrolysis from lecture 5. That turns it into a carboxylic acid. And then if you heat her, a carboxylic acid, beta to another carbonyl, it's going to do this really fierce reaction called the decarboxylation, where it does this like cyclic transition state, and you have all 3 of these arrows at once. It's very MCPBA-like. And when that happens, fully a CO2 will just pop off. This is a great like tack on to a mechanism question because it brings up lecture 5 stuff, and also you get this like fierce removing a carbon. Yeah, so decarboxylation here. And then the last one that I'll bring up is this reaction scheme called the monic reaction scheme. Kind of like how DCC is a synthesis reaction scheme, the monic reaction is used to make a beta amino carbonyl. Can you say that with me? A beta amino carbonyl. What we do is an amine and an aldehyde come together at pH around 5 to form an aminium. That's our lecture 5 reaction. And then because we're in mild acid, we can't make an enolate. So we are going to tautomerize our ketone into an enol, which remember is a nucleophile, just like an enolate, but it's just a little bit weaker. And then the core thing of the monic reaction scheme is an enol attacking an aminium. So you push down, attack your aminium. And when you attack your aminium, that makes this amine here. It is the only other reaction that we learned in the class that makes an amine. And this would never be on synthesis, but it's high key, probably going to be one of your mechanism questions. because again, does a great combination of lecture 5 stuff, lecture 10 stuff. The other thing that makes monic reactions tricky is oftentimes all of these functional groups are on the same molecule and they form like a weird like cyclic bridge, whatever. It's going to look funky, which is why you have to be really, really tight on your functional groups and be looking for it. So let's try this one. This is challenge problem 6 together. So do I see a beta amino carbonyl in the product? No, I don't see a carbonyl at all. So, this seems funky. But what's kind of the dog whistle that we're doing a manic reaction or a monic reaction? The pH being around 5. Exactly. Yeah, that's kind of our tip off. Because we're only doing amine stuff around pH 5, right? So, do we have an amine and an aldehyde? Yes, we do. Let's make that into an imine. So we have that. That's going to kind of connect these two. And the other big thing that seems to need to happen is we need to make a ring right here, right? Those are kind of the big bonds that we need to form. So let's do here iminium formation. That's the lecture 5 mechanism, but let's just draw the product of it to kind of try to visualize and piece this together. So in our product here, we're making this 5-membered ring. And now from here, we need to connect this star carbon over here to this circle carbon, right? So something needs to be a nucleophile, something needs to be electrophile. And this is the point in the monic scheme where an enol would attack the iminium, right? Enol would push in and would attack this iminium, and we would be basically at our product. But here, the iminium is going to be our electrophile. Is this star carbon a nucleophile? Do we have an enol? No. What do we have instead? What functional group is that? An enamine. And remember, an enamine is just the nitrogen version of an enol. We saw that at the beginning of section today. It went in and attacked something the same way an enol or enolate would. So the twist here of this question is you are doing an enamine instead of an enol. So you are going to have this enamine push down and attack as if it was an enol. And when that happens, that's going to close this ring. So there are going to be a few like final steps here, but that is like the trickiest part of here, this, of like clocking what's going on. The other one, which it's in the skill builders, but students often get thrown when they see a box formed, you know? But let's talk through kind of what's happening. Here we have this thing, dicarbonyl, easy to form an enolate, right? Super acidic. And then we have an alkyl halide. This is our SN2 alkylation. So what we do first is we add our alkyl group, 1, 2, 3, and a bromine here. But then we're still in base. We still have another alkyl halide here. And so it does a second alkylation. And those 3 carbons become attached again. So we have a box, but it looks like we got rid of a carbonyl. If we're looking at getting rid of a carbonyl, what reaction are we doing? Our decarboxylation. And so that's what these 2 steps are, the decarboxylation. And this was our alkylation. Last thing. The hard part in all of this lecture is seeing what's going on, is knowing these new functional groups These are the functional groups that you need to memorize and be on the lookout for all Lecture 10 things. So if you see an aldol or an enone, you did an aldol reaction. If you see a beta dicarbonyl, you did a Claisen. If you see a 1,5 dicarbonyl, you did a Michael. If you've added an alkyl group at the alpha position, you did an alkylation. If you're missing a carbonyl, you did decarboxylation. And if you have a beta amino carbonyl, you did a monic. With this, you also should know what the electrophile of each of these reactions are. So it's a ketone aldehyde for the aldol reaction. It's an ester for the Claisen reaction. It's an enone for the Michael addition. It's an alkyl halide for the alkylation. Kind of not applicable for the decarboxylation because that just kind of pops off. And then it's an imine here for the monic. And with that, we're done with sections for the whole summer. It has been lovely teaching y'all. Sorry, I feel like I have to really prod you in section, but I would hate to give you a boring section. So even if it's annoying, I would hope that it is a little bit more interesting. But it's crazy how much you'll have learned in 6 weeks. Like, truly, if you think back to the start of this course, could you have even explained to yourself what you're doing right now? Like, it's such a niche little world of doing all these arrows and building molecules and everything. And I'm sure it hasn't felt good. I'm sure learning this much this quickly, it feels like you're in boot camp and it feels like you're about to drop and you only have 1 more week left, and thank God. But you've really done a lot. Just the fact that you are thinking about this now, that's a big testament to do it in 6 weeks. And so proud of y'all. It's been lovely teaching y'all. I am looking forward to the last week, next week, and the review lecture on Tuesday, normal class time. This weekend, please take care of yourself, get rest, pick up paper copies of the practice exams before you go. And thanks for coming to section. Bye. Yeah.